So welcome back, everyone. Today, obviously, you can see a very big change in the setting. Well, there is no setting. It's just a blank screen, isn't it? So, actually, I've tested around with using screen recorders, and I actually found a screen recorder that functions well. So, today, pardon the background music or background noises. It might get a little tedious and annoying. But anyway. Today we are going to be revisiting linear independence and dependence and providing a more intuitive, or maybe less intuitive, but more useful sense to it, and how it actually can be useful, and how it's related to linear combinations. So let's get started. So let's quickly make the statement here, and also we're looking at the set. So we have some. Use this. You have some set, we'll call it S, and we'll say, obviously, some set of S, and we're looking at all the, we're looking at an infinite series of tuples, so V1, V2, V3, all the way down to Vn. Right, such that Vi, remember the reals, right? Doesn't matter which dimension at the moment. We're looking at a broad series of dimensions. So, yeah, just like so. So that's our set that we're looking for. And now let's make the statement. This is a statement that's really key to linear independence. So it's the fact that C1 times V1 plus C2 times V2 all the way down to Cn Vn, so you can see this is a linear combination of vectors, is equal to 0. So this statement, it would be, this set of vectors would be dependent if and only if, or if, right? That's sometimes denoted using, if and only if is sometimes denoted using two F's. If and only if at least one value of C1 equals something greater than 0. So, greater than 0. Or let's rewrite this a bit. One value of C1. It's kind of confusing, isn't it? At least one value equals C1 is greater than 0. So that's our statement here, right? So now let's look at another frame of reference of the spectrum. So we have this, right? But we also can say that a system or set of linear combinations of vectors is dependent when that set of vectors can be manipulated in some way to become a specific vector. We'll call it V1. So let's write that out. So it's going to be fairly similar. C1 V1 plus C2 V2 to Cn Vn. Or I need to be careful here. Oops. You get the idea. Plus C3 V3. Let me write this better. Plus C3 V3 to Cn Vn, right, is equal to some vector V1 v1. So that would make a set linearly dependent, right? Because there's some combination of these vectors that can be manipulated so that it becomes some vector v1, which is a member of this set, right? So now that we've made this statement, we can actually, it's pretty trivial to relate it to this statement, right? We can minus both sides by 1. First of all, yeah, we can do that. We can minus both sides by v1, and then we can get 0. Where can I write this? Let me put this to the side. So we can write C2 v2 plus C3 v3 down to Cn vn plus -1 times v1, right? Since we're minusing both sides of the equation like that. That looks horrible. Let me just make that look a little bit nicer. Plus negative, whoops, switching back, plus -1 times v1 equals 0, right? And this is essentially completely related to this because it does fit the constraints that it has at least one non-zero value for ci, right? Oh wait, I need to rewrite this. So ci, my bad, meaning any value of cx, any value of c. So c1, c2. That's just the meaning of ci. That's what I mean there. So yeah. So now the little less trivial bit will actually be relating this equation back to this equation. It's still fairly simple though. So let's say that v1 again. Let's say that v1 or c1 for that matter. C1 is some non-zero constant, so we can actually divide both sides by c1. So let's do that. Actually, I can. I don't know. I don't know where to free up space. Oh, perfect. That's actually very ideal. Anyway. Okay. So let's keep that equation in view. Okay, so let's relate it. So let's divide. Firstly, let's actually divide both sides by c1, since c1 is any. I'm saying that c1 is any non-zero constant. So we get v1 plus c2 over c1 v2 plus c3 over c1 v3 all the way down to cn over c1 vn, right? Simple as that. And that's obviously equal to 0. And then we can minus both sides by v1, and we get, I don't want to write this all, but we can actually rewrite that one here. So we get, now we get negative v1, right? And we can multiply both sides by -1 to cancel the negative terms. And these all become negative. This becomes a negative sign. This becomes negative, right? So basically what we've done here is we've related it back to this equation. Back to this equation here, right? Because this technically is, because even though it's negative, we can just say it's plus some negative constant, and we can call this some arbitrary constant, C1, C2. So we can set this equal to C1, right? Some arbitrary constant. So yeah, so we've basically just related it back to this equation. Obviously it might look a little different, but it's still the same concept. So that's pretty cool. right? Now this might seem pretty confusing, but let me give you guys some examples just to see how this can be useful with this new tool that we found. Okay. Well, let me just add that if the only solution to this equation here is that all values of c are equal to 0, then that means that it's independent. If at least one value is greater than 0, though, that means that it's dependent. So let's look at one example. Okay, so let's look at one example. So let's say we have the set of these vectors, or yes, vectors, why not? Vectors. So we have 3, 2, -1, right? And then we have, actually, let's make this a little more simple, so you don't have to do too much work. Let's use 2D equations. Anyway, I don't want to quickly start off with 3D vectors in 3-dimensional space, whatever. So let's start off with 2-dimensional vectors. So 2, -1, 5, 6. I know it's pretty trivial to see whether these are independent or not, or dependent or independent, because all you have to think about is one of these numbers scaled to get the other one, and it's obviously independent. But it's actually good to see if we use strategies, we can see that this will be useful for like vectors in 4 dimensions. That's how cool it is, because all you have to do is solve a system of 4 equations. Well, yeah, I'll just get to that. So if we plug it into this equation here, so we only have 2 terms, so we get some constant c1 times vector 2, -1, plus c2 times this other one, 5, 2, 6. That's equal to 0. Right? So again, if both of these values of C1 and C2 are 0, then that means that this equation that this set of these two vectors is independent. If one of these is like 1, for example, then that means it's dependent. So we can actually put this into a system of equations, right? Because if you multiply these out, you get a system of 2 equations. But we can actually directly do that. We don't have to multiply them out. As we learned from matrices, we can actually use the Gauss summation, or sorry, not Gauss summation. We can use Gauss elimination. So let's combine these two vectors into one matrix, one augmented matrix for that matter. So you can think of these as the coefficients of C1 and C2. Let me put this away. Five, 6, right? And then it's equal to 0, 0. I forgot to mention that the reason it's both zeros is because this is the 0 vector, so it can be bolded, right? That's the 0 vector, so all terms in there are 0. In this case, there are only 2 terms, since it's a system of 2 equations. Okay, so remember, we want to put it into reduced row echelon form, or maybe we can just do row echelon form, but we'll use reduced row echelon form. Oh, we'll see. So that means we can start off by turning this into a 1, or a 0. So we can actually multiply this by -2 to add these two rows. So we can write this out as we used in our strategies in the past. So -2 times row 2 plus row 1 plus row 1. Changes are directed to row 2. Okay, so let's do that. So we get negative 2 times this row. So this becomes 0. This remains unchanged, remember? Okay, this becomes 0, obviously. Negative 2 times 6 is negative 12. Negative 12 plus 5 is negative 7. Negative 7, and this obviously remains 0. Okay, so actually we could just end this here. So actually we can obviously tell that this is going to be 0 since we divide both sides by negative 7. This becomes a 1, and this means that the coefficient of 1 here, which is just C2, that's equal to 0, right? So we'll check to see if the next one is 0. Okay. So second change, this is done for. We can just erase that. And we can, I'm gonna make that look a little nicer. What did I just do there? We can also erase this. We don't need that anymore. That's our new equation. So now what we can do is we can convert this into a 0 as well. So actually this is relatively simple. It's trivial, so we can just multiply the second row by negative 5 and sum the two rows. So negative 5 times row 2 plus row 1, and the changes are directed towards row 2, or row 1, my bad. Okay, so let's do that now. So now we can just sum the two rows. So this becomes, this row remains unchanged, right? And then we get, okay, so negative 5 times 0 is just 0, so we just remain 2 here. And then negative 5 times this is just negative 5 plus 5 is 0. So that's what we get there. We divide both sides by 2, and we actually get a 1 here, and that's equal to 0. So as you can see, this is row echelon form, reduced row echelon form, because we have 1s here and 0s here. So we can now see that both are equal to 0, and thus making these two vectors, the set of vectors, independent, which makes sense because you can't multiply any constants by these to get the other. Anyway, hopefully you enjoyed that video. Hopefully it gave you a bit of intuition, and hopefully it made you actually interested in this, because in the past it didn't seem very useful, but now it's pretty interesting. So hopefully you enjoyed, and I will see you in the next few videos. And also, hopefully this, I think this, personally, I think this is a much better system since my hand isn't in the way of my writing, which I noticed in the past videos. So thanks for watching, and bye-bye.